that's happening. See this, and when you see that circle go away, that's the last one. And there's a lot in this notebook now, but at least we'll have it preloaded. Again, it's just runtime. Run before. You can do it with Control F8 as the hotkey, and great. We're all caught up and there are no errors. Okay. Now notice, just to keep things simple, I've been doing functions. That's when we say, let's see if I can find one up here. Sorry for scrolling. I know that's always annoying. Here we go. So when I did my NumPy-based power transformer, I just have it as a function with def. But there's a lot going on with the quantile transformer. And so I felt it was better to do it as a class. And you notice I went on ahead and followed the conventions of scikit-learn with that, fit and transform. And then I have some reporting functions also, methods. So just so you know, when we're talking about a standalone function, we call it a function. But in Python language, and it's okay if you forget this, it's no big deal. If we have a class and there are functions inside that class, we tend to call those methods because they're methods of the class. But so in quantile transformer, what we have is we can map to different types of distributions. And so here I have the default to be normal distribution. And then we have these buckets basically of quantiles. So I have n quants here. And this is a cheater method. If you want to see how to do this completely elegantly, the most thorough world-class advanced coding, you go look at the source code for scikit-learn. I did this tried to do it from scratch. I hit a conceptual shortcoming, and I had to go look in their code. And when I finally saw the step that I was missing, I was like, that's awesome. it really clarified it, but I don't look in the scikit-learn source code very often. And I was kind of glad to be forced to, because it's really very well written. Now, there's some things they do, you might not appreciate it until you've been in more of a production coding environment, but I really like the way they code. So here, this is a trick when you're doing classes, in case you haven't gotten to this in Python yet, where I'm saying self trans type equals trans type, where I've passed in trans type, self.enquants equals enquants, self.eps, or for epsilon, a small value, equals eps. Now, the reason I'm doing this, now, if I make an instance of this class, all of these will be available to the other methods. But this init function, init method, the function, is going to be run when I make the instance of this class. This stuff gets run automatically, and then once that instance is created, I can use these methods. So when we're fitting, let's go through this part. There's a number of points, and that's going to be equal to the length of the data that we set in. Now you notice I'm not sending the data in up here, I'm sending it in here. And then I also, to make this available later, I set both of these equal to the instances. You may notice that sometimes I will do this when I don't use it somewhere else. It's good to remove it when you discover that, oh, I don't need it everywhere else, because it's just taking up extra characters in your code. The more reduced you can make your code, the better, as long as it's still clear. So here, this is, I call this drefs, but it's just a linear spacing of the original data. I'm basically really just creating bucket points, or points on a scale. That's all this is. but it's important to the rest of this. And how am I doing that? I'm taking the number of points -1 because of the way Python works. And I'm just saying for x in range self.number of points, take x and divide it by the actual number of points. Well, the great thing about this is really, if to the mathematical observer, all this is going from 0 to 1 in fractional amounts, okay? That's all that did for us. Now this next one though, we're saying, well, that's one scale. Now I'm going to take the same scale from 0 to 1, but instead of going by the increments of the original data points, I'm going to go in increments of the number of quantiles I want. So it's kind of like saying, imagine you have 10 buckets on the floor, and we want to go to 5 buckets. So let me put someone on the spot. Okay, I'm going to volunteer someone. Greg, if you can come off mute, and it's okay if you can. How would I take 10 buckets to 5 buckets? Now, sometimes, oh, there he can. Great, Greg, just take your best guess.
How would you take 10 buckets to 5 buckets?
And try to still keep it in some kind of order. Okay, now think of it as numeric. I'm not being very fair to you. Let's say the 10 buckets are, we've got the smallest oranges in bucket 1, the next largest group of oranges in bucket 2, all the way up to, in the 10th bucket, we've got the largest oranges. Now I've got to organize those into 5 buckets of increasing scale. What would you do? I'm not being a very nice teacher today to put you on the spot.
So there's got to be some sorting that has to happen, or it's already sorted at this point?
Well, it's already sorted. Yes. We already have the 10 buckets. Is the smallest are in bucket 1, the second smallest bucket 2, the largest are in bucket 10. But we've got to put all those in 5 sorted buckets of size.
So there's got to be a divider divided by 2, but I can't really see it yet.
Just here's the best way to do it, and y'all can all help Greg. Picture the buckets really on the floor, and you've got to consolidate these 10 buckets into 5 buckets. And so
you increase the range or the number of sorted oranges in this case into 1 bucket. So you're increasing. So if you're starting from, if you had, well, these oranges, let's just call them A, B, C, and the next bucket had D, E, F, you're going to combine D, E, F with A, B, C to reduce the buckets in that way. So you're taking and enlarging your number range to reduce the bucket sizes.
There you go. But so which of the 10 buckets do you put in the first of the 5 buckets?
That's the challenge.
Now Greg can answer, or any of you can answer. Now I guarantee you guys, there's 2 failures going on. Either I have not clarified it well enough, or you're overcomplicating it. It's always one of those 2, and it could be both. So I assure you, and Greg, you might just be nervous because I put you on the spot here. It's quite simple. We just got to we still need sorting of smallest to largest, but we got to put those, we got to consolidate oranges from those 10 buckets into these 5 buckets.
Well, would you take, okay, if you have buckets, literally, I'm thinking buckets, numbers on the buckets, 1 to 10.
Yes.
You're going to take 1 and 2, which are the closest ones, and put those together, and then 3 and 4, 5 and 6, 7 and 8, and 9 and 10.
So 1 and 2 go in which bucket?
They go in the 1 bucket, because if you're putting them all in 1 bucket, you're going to put 1 and 2 in the 1 bucket.
Yeah,
Then
and
you're-
I should have said this. Imagine the 10 buckets have 1/10, 2/10, etc. And the 5 buckets have 1/5, 2/5, etc. So Val's right on the spot here, right on point. You take buckets 1 and 2, and you put those in bucket 1 of 5 for the new 5 buckets. You take buckets 3 and 4 of
3 and
10.
4 and 2 of 5.
Exactly. Now, let me tell you all a dynamic that happened here. Greg could have done this, but because I put him on the spot, his emotional level was up. And Valerie wasn't on the spot, so she had less emotional energy about being put on the spot and figured it out. And Jonathan helped us get there. So yeah,
No, see, the difference is I'm making soup this morning, so I'm already thinking of ingredients, and I got to put how many of my 8 cups of vegetables in. So I'm on the roll with that already. So don't worry,
Awesome.
Greg, you're great. I just am doing soup.
it really is. It's a cooking thing for sure. It's a kitchen thing we were talking about. No.
So I guess it's when you say it, Valerie, it's pretty easy to imagine. So I can definitely imagine it. Now I'm curious about how to code that, like combining bucket 1 and 2, then 3 and 4, et cetera, et cetera. So now you got me curious, Tom.
Excellent, excellent, good, Greg. That's what the real point of this was. And here's the cool thing. These 2 steps that I'm highlighting on the screen, they were just prep for what we're talking about. So this is the original 10 buckets, and this is the new in quants bucket. We'll just say it's 8. And let's just say, for argument's sake, this was the 16. This is 16 original buckets. Now here's how I do it. I'm going to put the data. And if you go look at the NumPy interp function, you'll see this firsthand. And this is a great thing about Google Colab. I don't know if Jupyter notebooks always said Jupiter, but it is Jupyter, the way Jonathan says it. It brings up these nice, handy reminders. And by the way, I can't always remember these, so I have to go look them up. But it's saying, if I want to interpret, this is the new X's, and here is the original X and the original Y. So I'm looking for the data splits, like with the buckets of oranges, that will go in. Here are the new buckets. So this defined both the bucket numbers and the oranges. And this is saying what oranges will go in the new buckets. Now, we can imagine if we get exact enough, the smallest oranges in the first bucket, they weren't all the same size either. So if we had to say put 10 buckets into 7 buckets, we might have to get those oranges laid back out and really measure them, get them in an assorted order and measure them, and then figure out how many total oranges we had and put them. Well, this is doing that all automagically for you, but it's interpolation. That's what that stands for. And we're just linearly interpolating into new buckets. So imagine we've laid all those oranges out from the 10 buckets. We've sorted them by exact order of size. And then we have to figure out now, oh, I got to put these 10 into 7. That's even harder. So I take the total number, divide it by 7. I drop those in the bucket. This is all doing that, but through linear interpolation. And why is this important? Because now in code, I can change the parameters at will. Now, what's amazing is this is just the fit part. Now we have to actually do the transformation. And this is, when you see what fit and transform mean with modeling, it's very similar to this, but when we're talking about these scaling mechanisms, it's a little different. By the way, guys, that mechanism word, perfect word for what we do. Math machines. I love it. By the way, now this can be new data, but we're probably using the same data. If it's on the, if we fit with the training set, now we're going to transform with the same data, but now later we can use this new fit that we have defined by all of this, where we've rebucketed. We can use that for new data coming in, like the test set, but we don't refit after that point, only on the training data. Also, you notice I'm taking great care with this. This particular lecture is going to help us with future modeling lectures in using the modules. That's why I'm taking great care to describe fit and transform for you. Okay. Oh, wow. We have another interpolation to do here. So here I've got the quantiles from up here. They're my new x for this next interp function. And these q refs, what are those? Those are that, whoa, Tom, here, the self-quantiles were the resulting y's. Now, try to stay with me mathematically. By the way, this is an excellent thing to do. You're listening, you think you understand what I'm saying, but maybe some of this is going over your head. What do? You break this down, you visualize it more, you find ways to make plots of it. You'll get it. Even if you think, you know, Tom, based on your recent posts and everything, I'm beginning to think maybe quantile transformation's not all that. Well, in some cases it will be, but the skills you learn by learning to visualize this and really understand it as deeply as possible will carry over to multiple other things you need to understand. Linear interpolation and inverse functions, super powerful to get good at, super useful to get good at. So again, here's what I'm saying. Original x, but that was our y. Now we're going to go y versus x, or excuse me, this is x versus y. Well, don't we usually say the dependent variable versus the independent variable? Yes, but we can imagine. We're just flipping it. We're saying, I'm treating this as x, which was my y up here, and this is my y, and I'm sending in the data. Why? Because I'm going to get Q data. In other words, I'm going to find, this is trying to say this. Hey, Lacra, how are you? I'm trying to say this in a way it'll be super clear. I'm trying to map these as cumulative probabilities. Now let's go back to something. I'm going to use this artful graph here on my background. Look at me in my camera here. Okay, here's a probability distribution function. Oh, I have this above. Let's go look real quick. Up here, I define mean, standard deviation, probability distribution function, which I was just trying to draw, a cumulative distribution function. Now you could look at all this math, hopefully, and understand it from there, but we're actually going to look at some visualizations of these. Then I have a histogram function I make all this just so you know what's going on if you use one from scratch. Then I have this create distribution function that uses those above, but I just want to show you. Here is my fake distribution. Just double check something real quick. Okay, sorry for that. I'll go back here where we were. Okay, so I just show how to create that. Now here's the thing. I want to create a probability distribution function. So this is me just cycling through points for a certain number of sigmas. This is a long tail. This is the number of standard deviations. I want to go before and after. I'm literally just plotting out a bunch of values. So, I mean, I'm creating a bunch of values so I can plot them. And I use a smoother. Don't read too much into this. This is just some tricks I'm using to plot that probability distribution function for you. So you can go through these on your leisure and ask me if you have any questions. I think we went through this a lecture or two ago. But imagine now that I want the cumulative distribution function. Well, I'm going to go through here and I'm going to create little panels, very thin panels under this curve. And as I add the values of those panels up, what's going to happen is the cumulative distribution function is going to go just like my pointer's going. And then it's going to keep adding up. And that's what the cumulative distribution function looks like. So how does that matter? If you will suspend your, if you will just push the I believe button, this is a very cool way to say, I've got these and I've got the data. Now I'm going to say, what is the cumulative probability of those occurring? That's all that's happening. Because this was a histogram, remember that? This was some distribution of data that we sent in. And I am just remapping the cumulative probability of it happening in the new buckets. Like, what's the probability of these orange sizes existing? It's here. It's here. It's just a new function from the cumulative probability of those occurring. Okay. Now, if you're new to NumPy and using mask, this is going to seem like magic to you. But NumPy just does so many amazing things for us. So let me explain. If it's just saying, for all the Q data that I just created, if for all the values that were 0, I'm going to set them to self-epsilon. This is just a way to deal. Yogita, you're there. Good. I'm cheating. The mathematical functions we're going to use, they can't handle 0 exactly. But they can handle a really small value that's close to 0, my epsilon up here. So what do? I just say, yeah, it's, even if it's 0, it's going to be epsilon. Now, if it's exactly 1, oh, the mathematical functions we're going to use also can't handle 1. So I'm going to make them just a tiny bit smaller than 1. By the way, I could have used a billionth here. Probably would have been better still. But then it causes problems in the visualization that I didn't want to deal with. So I cheated, with the epsilon I chose. Now, if you go look at what the scikit-learn coders do, you'll come back and say, Tom, those guys are so much better than you. Yeah, it'll be like if you're in the last thing, Dara Child saying, I was too intimidated to work at NASA. Dara, you would have been fine. I just was being lazy though. I didn't want to create so much code for the book. So these are just mathematical conveniences. And then I go through and I scale all my, this is amazing here. I'm rounding, but what am I rounding? I'm doing this is the most amazing part, and I'm totally cheating using NumPy. I could have coded this from scratch, I just didn't want to. This is an inverse cumulative distribution function. We're going from cumulative probabilities back to probabilities from like a probability distribution function. That's the NumPy magic, which is probably the SciPy magic going on here. I'm rounding it to 8, right, with NumPy round on the whole array. And then I'm taking that NumPy array and turning it into a Python list. Now, here's the cool thing. If it's a uniform distribution, I don't have to do this. Literally, those cumulative distributions are, those cumulative probabilities are my new distribution. And so I've got my scale data from either, depending on the type here, and I just return that. And that is the quantile scale data. Now, this is the hardest thing I've taught y'all yet. Actually, I should put it this way. This is all very simple, but it's not easy. Here's what I mean, and this is a learning technique I hope you all master. If you break down and plot out every one of these steps and read about 3 references, because I'm trying to explain it super clearly, but I may still be missing something. When you really need to take skewed data and map it to normally distributed data, this is super powerful. How often will you need to use it? In the famous words of Bill Murray in the first Ghostbusters, when Dan Aykroyd asked him how they're going to pay for all this stuff, Bill says, I don't know. I don't know. I don't know how often you might need to use this, but if you take the time to really understand it, the efforts to understand each simple step and see how it all goes together, each step will seem simple, but understanding how it all goes together, it's not easy, but if you take each step and understand it and visualize it, and then see how they come together, you'll go, oh, literally, it's just what Tom was saying. As I map those buckets to a new number of buckets, and it's always a smaller number of buckets in this example, by the way, I'm literally taking my original distribution, I'm redistributing it to my number of quantiles. I am then mapping it over to a cumulative distribution function. And once it's there, I can inverse map it back to the normal distribution, or just simply to take that to my new uniform distribution. It's going back and forth between probability distribution function, cumulative distribution function, and back to probability distribution function. Again, now I could have plotted all that out for y'all, but we'll do a little bit here. Okay, then I have report the quantiles, report the references, report the Q data, report the scale data. Again, the Q data is this cumulatively distributed quantiles over in the cumulative distribution function. I'm thinking back when I was at y'all stage, I'm really trying to explain this clearly, but if you're missing some of it, I don't want you to feel bad. Please don't feel bad. This is, I'm trying to describe it very simply, but I can imagine where I'm losing you, and I hope I'm not. Okay, I think I ran this, but I'll run it again. Okay, now we have this data. Now let's look at it carefully. These are some weird, this is just a slightly weird distribution. Notice I've got, if it had been uniformly distributed, I would have said, oh, 0, 10, 20, etc. Notice I'm only skewing it a little bit here. Now I'm going to take this distribution of data and I'm going to normalize it. I'm going to make it more Gaussian, in other words. And I'm going to turn the 10 buckets into 8. So I do my instantiation of our class. Then I do the fit with this data. Then I do the transform, and there's my scale data. And if we run this, and I'll just go ahead and run it because it'll reproduce these. If you were to, this is just 1/7 going from 0 to 1. Okay. And why 1/7? Because think about it. If I have 8 quantiles, we're looking at the number of regions between the 8 quantiles. If I have 8 numbers, there's 7 groups between those numbers. So that it's always one less for number of buckets. But I start at 0, of course, and go up. So there are 8 numbers here still. But if you look at these, each of these are 1/7, 2/7, etc. Now that you see my quantiles, if you look at this carefully numerically, you think, oh, well, that's all these are mapped the same. But what you've done is you've taken that original data here and you found the quantiles. So you see, this should have been like a 14, but it's smaller because of that 5. Now you see, I'm back to 0 to 1, but I bent it again. Look at, if we go backwards here, oh, yeah, that's mapped as we would have thought. Now I'm going back to the 10, but in the cumulative range. And you see that, oh, as I approach that 5, things got skewed a bit, probability-wise, cumulative probability-wise. And now, when I look at the scale data with that inverse going from cumulative distribution of probabilities to individual probabilities, aha, I see that it is different on this end than it was over here, but look, it has scaled it normally. So here was that original distribution, and here's what it looks like after I scale it. And I apologize, I just got bars touching each other. I should have fixed that, but all that means is there's multiple bars overlapping because of how close they are. And you see it's not perfect Gaussian. You see this part over here, but it's remapped adequately. Well, this is really this isn't even a toy example. This is like a single Lego, like, oh, here, play with these 3 Legos, okay? It's or maybe 10 Legos. But now let's do something a little more serious. We're going ahead and use, oh, well, here I'm just comparing, I was just comparing my results to their results. I think that's what I did. Yeah, I'm just showing that, hey, what we did above, which is simpler to look at code-wise than what's in scikit-learn. Yep, we got what they got. Now, when we go a little more complicated, we don't get as close. We get pretty close. So if I'm really going to have skewed data, I need a function that'll create some real large amounts of skewed data. And if you guys get good at using the beta distribution, you can create any shape distribution you want, including a normal distribution, a Gaussian distribution. But there's a weakness with beta. The X part always goes from 0 to 1. But now you know how to remap that with that interp function, okay? Or other ways too. In other words, once I have from 0 to 1, I can even just use standard scaling to move that around. So that's all I'm doing here. I've got the beta distribution first to just create a beta distribution. Now this, when I instantiate, well, by the way, if you've never been exposed to the beta distribution, you know what, I want to show you all something. This is so beautifully done on Wikipedia. So I'm just going to take a little extra time. And if it takes us another lecture to go over this and y'all want more visualizations, we can do those. But I would ask you to help me with LNID. I'm going to pull a window over here shortly. Data distribution, please. Yes, excellent. I'm going to show you all this brilliant demonstration of the beta distribution. Here are the, we use two parameters, alpha and beta, and it can create these different shapes when you have these different values of alpha and beta. And you can see that we get a really nice skewed distribution when we have 5 and 2. And if I flip the 2 and the 5 here, it'll just skew it the other way. So this is the one I use mostly. But let me show you how dynamic, how powerful this is. I know this, let me see if I can, this, oh, sweet. Okay. Look, it's just cycling through values of alpha and beta. Isn't that beautiful? How many different shape distributions you can make. And all you have to do is use scaling techniques to bend this. You can move this out of the 0 to 1 range and put it in any range you want using the scaling techniques we've already learned. All right, I'll bring that over here. Y'all, it's just that if you do beta distribution and then take the Wikipedia link, that's where that is. So in this instantiation, it's good. I'm going to show this some more. Here is the, by the way, I know this is one of the harder lectures we've done, intense math, all that. Here's the actual distribution, but there's a constant here, and that has to be created by a integration. And so I'm trying to show y'all where that happens. Basically, to get this may take 2 lectures, guys, but it'll be worth it. I'm trying to create that when I actually want to produce individual values from the beta function. Here's the x I send in between 0 and 1. And then here's that function, but see this self.b? That's that term that was divided by here. Okay? And it is self as a function of alpha and beta. So keep this in mind, the simple, elegant part here, this 1 over b, in the init function, I take the time to go ahead and calculate that. But I have to do it through integration. So I say the width of my panels is 1 over the number of panels, and I have that as a default value here. I also have the number of points defaulted to 1,000. So all I'm doing first is creating this x. And it's basically for x in range 10,000. I'm just creating 10,000 points between 0 and 1. Okay, that's all that's going on here. In this point, I'm actually running the distributions of those. Okay, so I'm saying for each x times my alpha minus 1, it's that other function I showed you, times my 1 minus x, x raised to the alpha minus 1, times 1 minus x raised to the beta minus 1, times the width for x in this x. All this is doing is numerical integration. It's adding up these tiny panels. So when I get that probability at that x, I'm saying there's a panel width, and that's an area under the beta distribution curve. for this number of points. Now, I'm kind of stuck with that number of points once I do that, but that's okay. And so I'm on the fly figuring out what that self.b should be. Well, this is an array filled with those panel widths, so the areas under the beta distribution. And I am summing those up to get my b value. And that's how I can fill the final point of that equation. Why do we need to do this? Because this b value, this b value changes depending on the distribution. So we actually have to figure it out on the fly. And then this way, if I just need a simple one, I can use these defaults. If I'm doing something special, I can define these accordingly. Okay, so now I want to make sure that I can create a skewed distribution using my beta function. So I'm actually creating the values I see. So here's where I define my function and its parameters I'll send in. And this is a type that I defined. It is a standard normal. I think, let's come to that in a minute. So here's how I create a skewed distribution. I say what I want the mean to be, what the standard deviation to be, and I also send in alpha and beta. Again, these only control the shape, okay? Now, I go through here, I've instantiated my beta distribution as BD with my alpha and beta parameters. I've got an empty array. We could have done this as a list instantiation, but it gets ugly, so I didn't. And then I say for X in the values that I have here, because again, I say the number of points I want, but I know I'm just going from 0 to 1. And I say X plus equals X. What I'm doing is saying for X in the values, based on the beta distribution, I'm going to take that fraction, because it's just a fraction, and I'm going to create a number of points. I'm going to multiply that by number of points for value. Well, it's never going to be the complete number of points for value. This is like a fraction of probability. But I'm just saying, create that many points of X. So this is literally just an integer multiplier on my current value of X. I'm saying create that many X's and extend. This is another way to append. You can just, you say I've got array 1, array 2, it'll literally make one array out of those 2 arrays in Python. So I'm just saying, build up this distribution of points, and build up these oranges of different sizes, basically. And for the probability of getting an orange that size, create that many oranges according to this. Well, now I've got that's great. I've got this distribution of data built up this way, but I don't like it being from 0 to 1. So I'm going to take the mean of X, all those points I just created. I'm going to find the standard deviation of them using those functions we previously defined. And I'm going to beta to standard normal scale. That's all that's happening. It's still the same shape. I'm just, instead of making the middle at 0.5 or somewhere between 0 and 1, I'm making the middle at 0. I'm just going to standard scale it. Well, let's run that. And then let's see what we can do. So here I've got a mean of 37, a standard deviation of 2. I'm going to change this. Let's say I've got this 2. I can create a skewed distribution now. Now this is hardcore fake data generation so that we can play with things. It can be really debilitating in your learning to wait for real world data when you can create fake data. But as you're seeing, I hope, the value of creating fake data is huge, but the knowledge gaining, if you know how to create the fake data, you understand what you're doing with the modeling and all the other steps of machine learning much better. I think I used 3 because my routine struggled with something downstream, but you see it's still pretty close to the same shape, and it is skewed. The average was supposed to be 37, and you can see the data is skewed. Okay. I'm going to rush through the rest of this because of our time. Now I'm using our quantile transformer and showing that I was able to map the skewed data back to normalized data. You can see, well, it mapped it, but look, it doesn't have as many values. It's more sparse over here. It's just like we expected if we were going to bend it. Now, do we ever falsify things in data science? Jonathan, what do you think? Valerie, do we ever falsify things in data science?
Certainly.
Yeah, we balance data sets by randomly sampling to rebalance the data set. If we artfully found there was a good reason to do it, we will remove outliers, as we talked about in our last session during Tech Time Chat. Hey, sometimes we are missing values. Excuse me, sometimes we might include certain outliers in both our training and test sets. You can't test on training, maybe a little bit, come on. You know, it's just the spirit of understanding what you're doing why. So why did I go through all that? To say, you know what? If we change the shape of this distribution, we just falsified that distribution data, but kind of falsified thing. I mean, when you look at logistic regression, yeah, we're bending that space so that we can create groups, right? And by the way, the cutoff doesn't always have to be 0.5 when you're trying to classify things. If you've gotten to that point in your studies, if you don't know what I'm saying, don't worry, but there's different ways we can bend things. So we just looking real quick, how does robust scaling affect skew? Let's look at that. So here's another skewed distribution, just to repeat it. And we did, we're going to do robust scaling. And you can see we went directly. Robust scaling didn't deskew it at all. So here's us comparing our quantile transformer to scikit-learn's quantile transformer. And yeah, it's not perfect, but it's still a good estimation. These are still just estimations, and you see it does cause a mathematical problem here. Okay, and this is just me and Guy going through our another example with right skewed data and then transforming it to scaled but normally mapped. Okay. Quantile transforming can be great when you feel there's a need to map skewed data to normalized data and scale it too, but use it carefully. And with that, are there any questions?